हार्मोनिक ऑसिलेटर का हैमिल्टनियन क्या होता है? कैन एनीबडी टेल मी? Suppose if you take a single harmonic oscillator, what is the Hamiltonian? Hmm. So let's go to the scratch. Just take simple pendulum. Can one write down a Hamiltonian for a simple pendulum? Kinetic energy, potential energy. लिखा जा सकता है ना?
Yes, sir.
So what is kinetic energy? P square by twice m. If the m is the mass of the pendulum. Now potential energy कितनी होती है?
हाफ m ओमेगा स्क्वायर x स्क्वायर.
हाफ m ओमेगा स्क्वायर x स्क्वायर. ये कैसे आया हमको थोड़ा बताओ. If you have some idea, how do you get this x square dependent? I'm not worried about m omega square, but I'm worried about x square because potential is a function of position. वो x square dependence क्यों आया? And what did you do so that you got a x square dependence? That's very important. Yes.
So we approximate that any given potential by doing the Taylor series expansion, and that first order term is zero as it is minima over there, or like that. And
Okay. मिनिमा होगा तो फर्स्ट ऑर्डर टर्म जीरो हो जाएगा. Why?
so first derivative, sir.
Yeah, but your second is also derivative. Second derivative.
Second derivative
फर्स्ट
will be
डेरिवेटिव जीरो. नहीं, फर्स्ट डेरिवेटिव जीरो हो जाएगा तो सेकंड डेरिवेटिव जीरो नहीं होगा.
no, sir. If it is not a saddle point, second derivative to zero नहीं होगा.
कैसे? This is what I'm worried. फर्स्ट डेरिवेटिव जीरो होता है तो सेकंड डेरिवेटिव जीरो क्यों नहीं होगा?
Sir, if it is a maxima or minima, sir, it will not be zero. If it is a saddle point, sir, then it will be zero.
So what is the difference between saddle point and minima maxima?
At saddle points, the curvature changes of that point
Okay.
from negative to positive.
Yeah, but you are evaluating at the equilibrium position only in the Taylor expansion, right?
Yes, sir.
तो मैं कह रहा हूँ if your first derivative at the equilibrium is zero, why not the second derivative in the equilibrium is zero? Meaning problem कहाँ है? Okay, no. Physically, I'll tell you what exactly is happening. Because if you look at the first derivative, your first derivative is like a force. So at the equilibrium, if you take, let's say, one-dimensional problem, and if you have only 1 degree of freedom, 1 degree of freedom meaning suppose you are just taking ions, there are no other degrees of freedom. So the force, because your first derivative of the potential is a force, and force you are going to look at the minima. So in one dimension, the force on the left and the force on the right, because there are only two directions in the phase space, they are going to cancel away if you have only 1 degree of freedom. But if you have more than 1 degree of freedom, suppose you have electrons and ions, now that's not going to be true. So see, it has first of all, it has only 1 degree of freedom. The only pendulum is going to oscillate in particular direction. So this is like a one-dimensional problem, and only 1 degree of one meaning you have nothing other than the pendulum. So your first order derivative, which is a force at the equilibrium position from left and right, they cancel away. But if you look at the second derivative, that's not going to cancel away. If you have only one degree of freedom. ठीक है. Actually, the fellows who are going to be taught by me in many body theory, they will see if I have an electron ion interaction, and if I'm going to look at a potential uh, due to ions, which puts a potential to the electron, that need not be zero at the first order, even though it is a Taylor expansion. Okay, so see, this thing you have to know now. The Taylor expansion, why first term is zero here for a simple harmonic oscillator, and your leading order term is only x square, not the linear term, because linear term vanishes. Okay, very good. And this is exactly, if I look at it in a pendulum case, I would say if you put a force, then the pendulum is going to it is going to make a displacement, and it will start restoring the position where you from where it has displaced. So that is something like a restoring force. So that restoring force is basically the same thing, your Taylor expansion, which is going to be potential is going to be x square, or your restoring force is proportional to the displacement. If the restoring force is proportional to the displacement, also the potential is x square. So either you can explain in terms of a restoring force, or maybe the expansion of the potential, uh, which leading order term is x square, not linear in x. Okay, very good. So you can write down a harmonic oscillator Hamiltonian p square by twice m and some x square dependent potential. Now, if you have this, you can solve this problem exactly if you have a single harmonic oscillator. Okay. Now, from that, you can derive a Lagrange equation of motion, or you can derive a Hamilton's equation of motion. And from there, you get equation like this: Ex double dot and omega naught square x equal to 0. So these are only the first term, and the third term, you're going to get only this, not others. And then I can write down gamma x dot. This I'm going to put it by hand because um, I presume now damping. Okay, because if the pendulum is in a medium, and if the medium provides a resistive force to the pendulum, the resistive force is proportional to the velocity, and there is a frictional coefficient which I put it by hand because this I have already explained you. Uh, if you look at in a longer time scale, macroscopic time scale, now this is what I can do. I am not worried about the model of the medium. Rather, the medium provides a force, resistive force, tremendous force to the pendulum. So this is just phenomenologically putting, and because this is what you observe in the experiment. The motion will slow down and it will stop after some time. Okay, so the equation exactly looks like this for a damped oscillator. And if you look at this, because this is it has a second order derivative, so you can go for a Fourier mode expansion, and then you are going to end up with this e to the power plus minus I omega t. You take that t dependence, take the double derivative, and then you'll end up with this. See, this is like doing a Fourier transform and getting an equation of this kind. This you have learned. Any uh, differential equation can be converted to an algebraic equation through Fourier transform. Okay. Now this has two solutions, and the solutions has an imaginary part and a real part. I mean, I'm calling real part provided omega naught square is larger than this. If omega square is less than that, then this can be also imaginary. Okay, so you have two solutions because if this look at the interesting part is if you did not have this gamma, then omega is real because it's just omega naught. Okay, so your solution would be e to the power plus minus I omega t. Okay, but so because there's a damping, now it gave me two solutions. Earlier also in case 3 case also it has two solutions plus minus omega naught. So I can have both, but here I have imaginary part also. So this is what it is. Now the motion gets affected depending on whether omega naught square is greater than less than gamma square by 4. So see, this is the restoring frequency, and this is also the frequency due to, frequency like parameter due to damping. I know one has to compare which is larger. And physically, if omega naught is much larger than this, then the your propagating solution, which is e to the power plus minus omega I omega t, will take over. But if this guy is dominant, then the damping part is going to take over. So one can just think of this. So depending on these two, one can define two time scales, fast and slow time scale. Hmm? Tau fast and tau slow, tau s. So your tau fast inverse, you can determine because the all energy. So the inverse of that is going to give you a time scale. So half gamma, this is what it is, because I can take uh, gamma by gamma square by 2 if I can take out common. So here it will be uh, meaning I gamma by 2. So I can take out that. And because this is tau inverse I'm saying. So tau inverse is related to this energy only. You can write down in this way. And then if you presume omega naught is much, much less than gamma by 2, then this will approximately go to gamma. So your tau fast is inverse of gamma. And tau slow is inverse of gamma by omega naught square, or your tau slow inverse is omega naught square by gamma. So both can be obtained whether omega naught. I have given both same. One should be larger, by the way. I'm sorry. So this cannot be the same. One is much larger, another is much slower. Okay, so your tau fast and tau slow, the two time scale depending on whether uh, your frictional coefficient or the viscous coefficient gamma is much larger than omega or much lesser than omega. Okay. Uh, Now, so case one, if I tell you the omega square is much larger, hmm, then omega 1 is real. Because omega 1 I have defined somewhere. Upper, I think. Yeah, omega 1. This omega 1, which is this square. So omega 1 is real. And your xt, because ultimately you have to look at the position coordinate, because the equation is position coordinate. So your xt is oscillatory with the frequency omega 1, and the dk is inverse of gamma, inverse of the um, damping coefficient. But suppose if omega square is less than gamma by 2, your gamma damping part is dominant. So your omega 1 is imaginary. So no oscillation, no propagating solution. The motion will be over damped. It will be damped out very fast. And the decay tau f and tau s. Okay, so one can have these two time scale. Um, okay, ah, two classes. Yeah. Okay, so this much exercise one can do it for um, damped oscillator by looking at the solution. Okay, and by the way, one can think of also if this is same. Okay, actually, see, I don't know. This can be taught in mathematical physics. Okay, if somebody might have done also in mathematical physics. So now my main part is once you know the preliminaries in the damped oscillator, come back to the response function part. The response function part is as well I said. See, this is x. So if you put a force, then your x is going to change. So this ratio for very small x is going to be chi of omega. Okay. So if you look at here, just go to the equation. You just go to this equation. Okay. So the inverse of this is basically going to be the response function. Yeah, because you can write down xt is chi t or x omega is chi omega into f of omega. Okay. So here you can write down this equation because there's a xt, and here you put a ft. So then this into x of omega equal to f of omega, and x of omega divided by f of omega is the inverse of this. समझ में आई? Huh? I'm saying if you put a force, the harmonic oscillator can be written with a right hand side ft. Now you go for Fourier transform. So this into x of omega equal to f of omega, correct? And x of omega divided by f of omega is the inverse of this. So immediately you will get a response function if you have a driven field. And your response function is exactly equal to this, which I said inverse. And so because mass was also there, so I pulled a mass. So look at your, one can write down this omega square I gamma omega minus omega naught square. This is omega minus omega 1 tilde and omega plus omega 1 tilde. And omega 1 tilde has both your imaginary part and the square root part. Okay. Now, if you take static limit, omega goes to 0, then this response function is going to be uh, 1 by m omega naught square. And this is static limit, low frequency. But if you go to high frequency, it is of course frequency dependent. Here there is no frequency dependent because this is natural frequency, or that is just a parameter root k by m. But here it is omega dependent. And you typically your response function is going to look like this, because I can write down this as a real part and an imaginary part because uh, just 1 minute. I can write down this. You look at this. This is the imaginary part. So I can multiply with the conjugate, and I can separate it out the real part and the imaginary part. So your real part is going to look like this, and your imaginary part is going to look like this. And I can plot the real part and the imaginary part. See, your imaginary part of the response function has two peak structure, one this side and other this side. And actually your imaginary part, these are all probability functions. Probability meaning You can think of, if you take one solution, this is just a probability. It's some distribution. And this is also a distribution. Inverted, but it's a distribution. So it has two peaks for positive and negative frequency because this is a second order equation. But the real part, and this is exactly near omega equal to omega naught. I'll tell you why this happens. And exactly around that point, your real part, it will cross over from positive to negative side. Okay, but here it is not. It will cross zero. So you already know now the response function, real part and imaginary part. Uh, and actually, if you put take the imaginary part and take the limit gamma goes to zero. I mean, of course, before that, now this imaginary part can be written as a two Lorentzian peak. See, these are peak which are Lorentzian with a width gamma by 2 and peak omega equal to plus minus omega 1 if they are damped. But if you take gamma goes to 0, then the imaginary part is going to give you two delta function peaks at exactly plus minus omega 0 with a weight. See, even though it would give you a delta function peak, because delta function peak doesn't have any width. And if it doesn't have width, your lifetime is infinity. So if you have a harmonic oscillator, the excitation of the simple harmonic oscillator uh, is long-lived, infinitely long-lived, because the lifetime is infinite. And that they are very, very well-defined modes. They are never going to decay, and they will transport either heat energy or some other form of energy. Um, I mean, if it can be taken to the transport phenomenon. Okay, but then I'm saying, even though they are delta function peak, they will have a weight, and this weight will be seen in some experiment. Okay, so now chi prime omega is positive for this, negative for this, and zero for omega equal to omega naught. And chi double prime is real odd in omega, two Lorentzian peaks, which reduces to delta function peaks in the on damped case. Okay. Now, anybody has any question at this place? Because I started with simple harmonic oscillator. I did not go from the scratch because I think everybody knows harmonic oscillator Hamiltonian and how to write down a differential equation. But thing is, once you have damping, then you can go for some time scales, fast, slow, and depending on that, you can go for putting a response function. And response function, you can do it by writing down the harmonic oscillator once you put a force on the right hand side, because it's a driven system. You have to apply force. And that is going to give you to determine what is called chi omega response function with a tilde or whatever. And this can be calculated from the equation of motion. And so because the response function, see, look at your response function is very peculiar, by the way. It has two solutions, two poles. Okay. That's what I was saying. Your response function, the pole of the response function is going to give you some interesting things. And in one case, you can get this energy of excitations. In other case, from the width, you can get the lifetime. Yeah. So if anybody has any question at this level, I can answer.
Sir,
Bolo.
so what those time scale gives physically?
Time dependent. I'll come to that. I'll come to that. Don't worry. Because I said because see you have two parameters. No, you have natural frequency, which is spring constant by m root over. Your omega naught is what? Omega naught is some spring force divided by mass square root. Correct. That is a parameter. It is not a variable. Your omega naught is not a variable. It is a parameter of the system. And other parameter is the damping coefficient. Now there is a competition between these two. And because of this competition, you have to have two time scale. Because one time scale, see, uh, uh, because see, if you don't have damping, you have only one time scale, and the time scale is infinite, and that is inferred from this delta function. See, if gamma goes to zero, the delta function peak. This is the delta function peak. Delta function. This is a zero width, zero width. So your time scale or time decay, I would not say decay time, lifetime of the modes, harmonic oscillator propagating mode is infinite. So means if you take the harmonic oscillator, those mode will be there for infinitely long time. Nothing is going to happen to them. And in physics point of view, these are uh, very good modes which can transport energy. जैसे मैं कह रहा था ना कि suppose you take a rod, an iron rod, and put it on fire, and if you model the rod with a harmonic, now these are the modes which are going to transport heat energy from one end to other. ठीक है? But if you have damping, then because they are going to compute, the damping is going to compete with natural frequency of the system itself. Then you'll have two time scale, and fast time scale is for the natural frequency take. Okay, so which one is what? Okay, so here if the damping coefficient is much larger than the natural frequency, your time scale will be dominated by the damping coefficient, inverse of that. But your fast time scale is your this guy dominates. Omega is much larger than gamma by 2. So your damping is small. So this time scale has a natural frequency also as a parameter. The gamma by omega naught square. That's tau s. So you have to have two time scale. You can't do any other. Yeah. And depending on your system, which one is taking over, so your modes are going to be described in those time scales. Yeah. Mm. Right, because here I can figure out the width of this peak, because that will be either tau s inverse or tau f inverse. Okay. So that is with you. ओके और कुछ सवाल है? Any other question, if anybody has?
Sir, can you please repeat the last thing, sir, that you said? My
No, no. What I'm saying, if you have a simple harmonic oscillator, you have only one time scale because your imaginary part of the response function is just two delta function. One will have positive omega naught, another will have negative omega naught. That's the energy of excitation or the modes which are having these energies, omega naught energy, because it will have only two pole structure, omega 1 by omega square minus omega naught square. So it will have two poles. One pole is at omega equal to omega naught plus, another is omega equal to minus omega naught. And they will have zero width. So these harmonic oscillator modes will have infinite lifetime. And in any transport phenomena, you need modes or excitations which will have infinite lifetime. Because otherwise, you will have problems. Suppose a mode decay कर जाता है. Suppose if it has, if this is width is very large, then the inverse of that which is a lifetime. So मान लो that mode is going to transport energy, and suppose if you are measuring and if you are looking in a shorter time scale, you won't see this mode. वो mode decay हो जाएगा उस time scale के बाद. So it may not be able to transport your heat energy or some other energy. समझ में आई? So a damped oscillator is something like this, because it is going to damp away. So it is not going to transport. It will transport up to some time, and then it will just decay. Transport, correct? Do you understand? I mean,
Yes, sir.
okay. So see this thing. A mode का मतलब क्या है? आपका even Ohm's law. Somebody is going to transport electrical energy from one end to other end, right? But if electron is not long lived now, let's say, or infinitely long lived नहीं होगा, then it will just decay. तो आपका एनर्जी, इलेक्ट्रिकल एनर्जी आपने करंट मेजर करने के लिए मुश्किल होगा, बिकॉज वो ट्रांसपोर्ट ही नहीं करेगा. Yeah, because if the electrons in a material is going to damp away, it cannot transport, and you will not see current or feeble current. बहुत सारे करंट आपका लॉस हो जाएगा. बेसिकली योर रेजिस्टेंस इज दैट. रेजिस्टेंस जो आता है ना ओम्स लॉ में, because your electron gets scattered, वो पूरी इलेक्ट्रिकल एनर्जी लेके पहुंच नहीं सकता, इसीलिए आपको जो करंट आती है वहां से रेजिस्टेंस आता है. रेजिस्टेंस जीरो होगा तो देन दोज मोड विल बी सच मोड्स व्हिच आर इन्फिनिटली लॉन्गली. तो इलेक्ट्रॉन इलेक्ट्रिकल एनर्जी लिया और पहुंचा दिया, सो योर कंडक्टिविटी विल बी इन्फिनिट. बट रेजिस्टेंस आ रहा है, मीनिंग इलेक्ट्रॉन इज नॉट ट्रांसपोर्टिंग द फुल अमाउंट ऑफ एनर्जी. कुछ तो डिसिपेट हो रहा है जो रेजिस्टेंस के फॉर्म में आपको दिखता है. होप आई मेक थिंग्स क्लियर.
Yes,
यहाँ भी हार्मोनिक ऑसिलेटर में भी वही होने वाला है. जैसे बेस्ट एग्जांपल इज फोनॉन्स. फोनॉन्स आर बेसिकली समथिंग लाइक हार्मोनिक मोड्स इन द लैटिस इफ यू टेक ए मेटेरियल. एंड आई एम सेइंग फोनॉन हीट एनर्जी ट्रांसपोर्ट कर सकता है. तो वन कैन राइट डाउन इक्वेशन, हार्मोनिक ऑसिलेटर इक्वेशन विथ ए डैम्पिंग फैक्टर, क्योंकि वहाँ डैम्पिंग तो रहेगा. और सिंपल, वेरी वेरी सिंपल थिंग इज सिंपल पेंडुलम. बट सिंपल पेंडुलम में प्रॉब्लम है कि एक ही रहेगा, बट यू कैन सी ऑसिलेशन कैसे धीरे 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 बंद हो जाएगा. So that's basically getting damped out, and your modes are becoming very short-lived modes. Okay, not long-lived. Okay. Now, कोई question? Any other question? Problem. हो देंगे, next class करेंगे. I can just tell you over damped case. देखो over damped case में I can take a limit. Over damping meaning आपका damping is dominant. So your tau omega tau f is much less than 1. और आपका actually if you look at the equation of motion, जो न्यूटोनियन मैकेनिक्स का न्यूटोनियन टर्म है x double dot, that is basically going to be, the contribution is going to be very little. So one can just throw away x double dot. Okay. And then if you don't have x double dot, your gamma x dot plus omega naught square x equal to 0. So calculate your response function is something very simple. तो आपका ओमेगा स्क्वायर और रहा नहीं. In the overdamped case, where the damping is much larger. Okay, and now for this, you can define a slow time scale because I can write down in this way, and your chi static this and something like this. So your chi omega can be written in this way, and you can figure out writing down the real part and the imaginary part. And if you look at from this, you can calculate chi double prime is the imaginary part divided by omega is pi chi static 1 by pi, pi 1 by pi pi मैंने multiply divide कर दिया है. And then tau s inverse by omega square plus tau s minus 2. And this is peaked at omega equal to 0. Okay, so आपका this is the width, and width tends to 0. It will be just a delta function, so one can do an integral over this because this is a delta function. This integral is going to be or this integral is going to be just chi static. So the pi I can take it this side and then do all frequency integral. This is going to give you a static response function. So in the overdamped case, you can learn one thing that which term to throw and which time scale is going to appear in the peak. From the peak, you can estimate the time scale. And the interesting part is if you take the imaginary part and divide it by frequency and go for all frequency integral, this is going to give you a static response. And this is like a sum rule. This can't be violated. ठीक है. मैंने यहाँ आपको एक चीज बता रहा था कि यहाँ जो काय स्टैटिक निकाला है मैंने, काय स्टैटिक is 1 by omega naught square. So see, these are basically going to appear as a prefactor in the peaked function, a prefactor. So a prefactor is basically going to appear in this sum rule. अब वो measurable है. Okay, so measurement में basically you crack down on this. And you can infer many things from here, whether your model is correct or not, or you have to do something more, etc., etc. Yeah. So this gets you which time scale you should look into also as an approximate way. Ah, bolo. Hmm. So we'll discuss maybe on Thursday the rest. Yeah. किसी को कुछ पूछना है तो बता. You can read through Chaikin and Lubinsky, chapter 7 or something, dynamics. Okay. So, any question or shall we just leave it? किसी को कुछ पूछना है? Yes, no. Okay, so I'll stop here. Yeah. Hmm.